Assalamu alaikum. Welcome to the lecture 12 of Unit First. In the previous lecture, we have studied resistance triggering, AC resistance triggering. This is the remaining part of that resistance triggering. As we know, this is the general figure of this resistance firing circuit. In case if this resistance RV is zero, the gate current flows from this resistance R minimum, this diode D, and the resistance RB. The value of this current should not exceed the maximum permissible gate current IGM. So we can calculate the Rm from this relation, that is Vm divided by R minimum should be less or equal to Igm, or we can say that our R minimum should be greater or equal to Vm divided by Igm. Similarly, the resistance Rb should have such a value that the maximum voltage drop across it should not exceed the maximum possible gate voltage, that is VGM. And this happens only when this Rv is 0. Under such condition, by using that voltage across this resistance Rb, which is equal to Vm into Rb divided by R minimum plus Rb, it should be less or equal to Vgm. Or we can calculate the value of Rb from this, that is Rb should be lesser or equal to Vgm into R minimum divided by Vm minus Vgm. The relationship between peak gate voltage, that is VGP, and the gate trigger voltage can be derived from that means VGP sine of alpha is equal to VGT, or alpha is equal to sine inverse of VGT upon VGP. Since we know that the voltage across the resistance RB is VGP is equal to Vm into RB divided by R minimum plus RV plus RB, or alpha is equal to sine inverse VGT into R minimum plus RV plus RB divided by Vm into RB. Since we know that VGT, R minimum and RB are fixed, that itself means or alpha is equal to sine inverse, since the only variable part resistance is here RV is equal to sine inverse RV, or we can say alpha is proportional to the RV, which means that our firing angle is proportional to the resistance RV. As RV is increased from smaller value, firing angle increases. But it should be kept in mind that alpha can never be more than 90. Now, the next firing scheme is the resistance capacitance firing scheme. In this RC firing scheme, our alpha is our alpha is extendable beyond 90 degree. Here, the supply voltage appears across the RC branch, that means RV and this RC branch. Here we are neglecting the discharge of the capacitor during the conduction period of the thyristor. Or we can say this circuit can be analyzed by the sinusoidal steady state response of a linear RC circuit. Now let us take the circuit of this resistance capacitance firing circuit. Firstly, we are discussing the half wave voltage, half wave RC firing circuit. Here, during the negative cycle, that means this will be negative, the source voltage, this will be negative, and this will be positive. Since SCR is not conducting, that means during negative cycle, this diode D2 will be forward biased. And this causes the charging of the capacitor C. That means during the negative cycle, that means if this is negative and this is positive, this will be negative, and this will, that means this negative negative, that means this diode is forward biasing, and this since the D2 and resistance RV, which is the variable resistance, they are parallel. Since the path across this diode D2 acts as the shorted path, or we can say the voltage across this RV will be equal to 0. Ignoring this branch, by thus it results in the ignoring of this branch. The voltage build up through this branch occurs only when this reverse voltage across this diode is emitted. That means during negative cycle, this capacitor gets charged with the upper plate negative, and this is the positive. Until and unless this is shown in the diagram as, that means this is negative cycle, that means this is here from -0 crossing instant to this -90 interval, the voltage across the capacitor, the capacitor builds up the negative voltage, which is equal to minus Vc. And at that instant, that is at omega t is equal to -90, since this is the maximum voltage across this source voltage will be minus Vm, and the maximum voltage that is charged across this capacitor will be minus that means this minus Vc is also equal to minus Vm. That means the potential across this diode will be 0, and this the potential across this diode will be equal to 0. Thus, the current across this diode ceases, and this diode D2 becomes reverse biased. And since the current across this ceases, now this resistance, the function of this resistance comes into action, or we can say now the charging of capacitor across this limb, that means this across this limb RC starts. This is the, that means this here by dotted line I am showing the voltage across the capacitor from this this crossing over to this -90. The voltage across the capacitor is minus Vc until and unless the current across this diode ceases, and this is now reverse bias. This is reverse bias until and unless when the zero crossing of this positive cycle starts, now the voltage again starts building up, or we can say this diode D2 becomes now a reverse bias, and the charging of capacitor increases until and unless this charging capacitor voltage becomes equal to VGT, where VGT is our gate triggering. That means whenever our VC becomes equal to VGT, triggering of SCR takes place. This diode D1 is used to prevent that diode D1 prevents large negative supply voltage to appear at the gate terminal of the SCR. Here the empirical equation is given by RC should be greater or equal to 0.65 T, which is equal to 4 upon omega, where the angular frequency omega is equal to 2 pi upon capital. Here, since Vc becomes equal to Vgt, that means this represents our triggering angle alpha. When the thyristor is triggered, the voltage across the load will be exactly the same source voltage. That's why from this to, that means from this alpha to pi, it follows this source voltage, and from 0 to alpha, since the SCR is not triggered, it behaves like an open circuit. The current across this path will be 0, and that's why this voltage across the load is 0. The voltage buildup across this capacitor depends on the time constant RC. Lower the value of resistance RV, quicker higher will be the value of this voltage VC, quickly it will reach the value of VGT, and lesser will be the value of alpha. This means higher the value of resistance, higher higher will be the value of alpha, lower will be the value of resistance, lower will be the value of alpha. Also we can say that lower the value of resistance RV, lesser will be the value of alpha, and more will be the output voltage. Higher the value of resistance RV, higher will be the value of alpha, and lower will be the average output voltage. Resistance capacitance firing circuit for the full wave. Here we have incorporated a diode bridge. In this circuit, the initial voltage from which the capacitor charges is almost zero. Here, charging of capacitor takes place through resistance R, and this charging rate depends upon the time constant RC. When the voltage across this capacitor becomes equal to VGT, conduction of SCR takes place. The conduction of SCR takes place simply by controlling the resistance R, or we can say simply by by changing resistance. We can change the charging of the charging rate of capacitor, or we can say alpha can change. Lesser the value of resistance, lesser the value of resistance, lesser will be the value of alpha, or we can say quickly it can charge up to that VGT value. Similarly, higher the value of resistance, higher will be the value of alpha, and lower will be our average output voltage. Next triggering method is UJT, that is unijunction transistor. Both resistance and RC triggering circuits give prolonged pulses. As a result, power dissipation in the gate circuit is very large. Moreover, those prolonged R and RC circuits cannot be used for automatic or feedback control systems, and such difficulties can be overcome by using this UJT triggering circuits. UJT provides us pulse triggering, and it's preferred as it offers several merits over R and RC triggering circuits. The power level in pulse triggering is low as the gate drive is discontinuous. Therefore, we can say this pulse triggering is more efficient. Also, these pulse triggering is more reliable and faster. Here first, UJT's construction is described, and then its characteristics are explained, and then its use as a relaxation oscillator for triggering SCRs is explained. This UJT-based oscillator provides constant frequency, sharp pulses with small rise time. This UJT is a three-terminal two-layer PN device. It has N-type semiconductor between two base terminals B1 and B2 with small p-type doping at emitter terminal. That means we have three terminal. One is this p-type emitter terminal, and another one is this base B1 terminal, and third one is this base B2 terminal. The emitter terminal divides the inner base into two parts, that is this RB1 and RB2. It's symbolically represented by this diagram, and its equivalent circuit is shown in this diagram.